Today's background is Ebor Falls. It's on the Guy Fawkes River in northern New South Wales, and it's on the drive from Urunga to Armidale. So Urunga is a little bit south of Coffs Harbour. You drive inland through a little town called Bellingen. It's a really nice place to stop for lunch. And then if you keep driving inland, you get to the edge of the Great Dividing Range. And at this point, it's actually an escarpment. So you drive up this really sharp escarpment. There's a whole pile of waterfalls on the drive up that you drive past. So it's quite nice. When you get to the top, you arrive in a little town called Dorrigo. That's a good place also to stop in because there's a rainforest centre there where you can do a walk, and there's a couple of really nice waterfalls on that walk as well. And then you sort of drive across over the Great Dividing Range to Armidale, and on the way through, you run into this on the side of the road, which is Ebor Falls. It's a nice falls to look at. There's a couple of them in a series running down the river, and it's actually a nice place to go hiking as well. The hiking was closed last year and probably is still closed for some of this year because of bushfire. You can see, a tree with some epicoric growth just up here. But hopefully it's open at some point soon because the sort of Great Dividing Range country in that part of New South Wales is a really interesting place to go hiking. So, what I want to do in this second half is come back to this idea of standard deviation that we had in the first half. And let me bring up some slides. We had this, we defined a standard deviation, and what we found was that if the mean of the distribution is zero, the standard deviation becomes a really simple expression. It's basically just the root mean square of the um, difference away from the zero mean. And that ability to write the standard deviation in such a simple way kind of inspires us to take our operators and define a new operator, which we'll call L bar, where we basically take our operator L and subtract the expectation value so that we can set the mean to zero, because then we've got a really easy expression for what the width of that distribution is. In order to do that, we need to know that we can basically shift the distribution for an operator back to zero mean without changing its width. So that's one half of what I want to do here. The other is, if we're going to redefine our operator in that way, I want to make sure that it doesn't change the outcome that we get for commutators, because that's going to be quite important in the next lecture as well. Okay, so I could easily go on to uncertainty in the next lecture and just say, oh, we shift the distribution, the width doesn't change, the commutators are okay, and you would have to take my word for it. I think it's actually good as young scientists to actually test a lot of things your lecturers say, and sometimes I also like to demonstrate them, and this one is one here where I really want to show you that this is actually true for these statistical distributions. It's also a good chance to get some idea of what you can and can't do with statistical distributions in quantum mechanics. Before we start on the algebra, you remember back in the first half, one of the annoying things we had was that we basically had to write a square root on every single line. After a while, you start to end up feeling like this. You can tell these guys have spent quite a bit of time dealing with the algebra of standard deviations in their time. And so what we tend to do to overcome this problem is deal with squared uncertainties. That way we don't have to write square root on every single line. And when we get to the end of the algebra, we can basically just take the square root of the final result to clean it up. So that's exactly what we'll do here. Let me bring up some paper. What we're going to do now is start working through the idea of defining a new operator where we set the mean to zero. So we'll start with just a definition for this operator. So we'll call it L bar, and it is really just going to be the operator L minus the expectation value of L. Now you'll know that L here on the end is a real number, and the two operators at the front are in principle matrix operators. Okay, so what we're really doing here is defining this thing as the real number for the expectation value times the identity matrix I, where that identity matrix I is really just a matrix with 1 on every diagonal and 0 in all the off-diagonal elements. Okay, so really what we're doing is just converting a number up to a matrix so that we can take a matrix being equal to a matrix minus a matrix. Okay, all right. often when we do the maths like this, the identity matrix on the end there is implied. So we will still just write it as L minus expectation value of L. So we're going to think about the squared uncertainty. And so that squared uncertainty is delta L squared. And we can write this thing using the expression that we arrived at earlier as expectation value of L squared minus the expectation value of L squared. And so all we've really done here is taken that expression a couple of slides ago and squared it so that the square root disappears. What we want to show in here is basically that if we define the uncertainty for L bar, that it is equal to the uncertainty for L. And in particular, actually, what we just want to do is show that the square of the uncertainty behaves that way, because we know if we take the square root, we will get that to be the case. Okay, so what we can do here is start by writing the square of the uncertainty of L bar. And we can write it in much the same way that we wrote our uncertainty for L just up here. So it would be the expectation value of the square of L bar minus the expectation value of L bar squared. Okay, so we're just using the same definition, but now with our L bars in there. We've specifically defined L bar so that the mean of L bar is 0. So the expectation value of L bar is going to be 0, which means that this thing is basically just L bar squared average. Okay, so it's really just the 0 mean, root mean square definition that we had earlier. We can now in here use our definition for L bar. So this thing will be open triangle brackets, L minus expectation value of L squared, close angle brackets on the end. So all we've done is just use our definition for L bar. And now we can work through and take the square of this thing in the brackets. So this is now going to be L squared minus 2L expectation value of L plus expectation value of L squared, average bar on the end. And then, as you remember, the sum of average, the average of a sum is the sum of averages, right? So this thing will basically be the average of L squared minus the average of L. Just to emphasize this, we're now going to have the average of L as this term for the expectation value, plus the average L squared on the end. Okay. Of course, you'll remember that the average of an average is just the average, right? In other words, average L is just average L, because the average of a number that's fixed is just going to be the number. And so what we can do is write this thing as L squared minus 2 expectation value of L, expectation value of L plus expectation value of L squared. This term in the middle here is minus 2L squared plus L squared on the end. And of course, this ends up being L squared minus L squared on the end there. And of course, this thing is really just delta L squared that we defined right up here as equation 1. Okay, so what we've basically just shown is exactly what we need to show in here, which is that the uncertainty doesn't change, or the width of the distribution doesn't change if you change the operator such that you set the expectation value to 0 in there. It's a result that we'll need for the next lecture, and you'll see that one come up again. So one other thing that I need for the next lecture is to know that I can shift an operator by its expectation value and not adversely influence the commutator. Okay, so what I want to be able to show is if I do the same transformation for two operators, A and B, that I still get commutators that make sense. Okay, and so because here I'm going to need two commutators rather than just one, I'm going to call them A and B rather than L, but expect that they have the same properties as we had before. So let's work through the algebra on this one as well. Let's start by defining A bar and B bar here. So A bar is going to be A minus the expectation value of A, and B bar is going to be B minus the expectation value of B. What we're going to do is we're going to start with the commutator with the bars in it and see if we can get back to the straight commutator. So let's start here with A bar, B bar. And the first thing we're going to do is basically write this as the commutator of the two definitions. So this will be A minus expectation value of A, comma, B minus expectation value of B. The next step in here is basically to expand out this commutator. Remember, if we have a commutator AB, it's AB minus BA. So this would be, oh, hang on, wrong brackets. Let me go to curly brackets. A minus expectation value of A, B minus expectation value of B, minus B minus expectation value of B times A minus expectation value of A, like so. And so the next step in here is basically just to expand all these terms out. And at this stage, I'm going to expand them out conserving order because some of them are operators and I need to be careful about conserving order for operators. So this will be A times B minus A times expectation value of B minus the expectation value of A times B plus the expectation value of A times the expectation value of B minus, let's put these in brackets for now and we'll use curly brackets just so we can keep track of what's going on. We will have BA for the second one, BA minus B times expectation value of A minus expectation value of B times A minus expectation value of B, expectation value of A, like so. Okay. We can rewrite this in a moment, and I'll move my equal sign over so I've got a bit more room. We can rewrite this in a moment just by taking away the brackets. So we enact the negative between the two brackets on all the terms in the right-hand side. But now we realize that for some of them we can swap the order and for some we can't. For any product there that has two operators in it, we can't just swap the order of the two operators because they're both operators. But any of the products there that have an expectation value in them, the expectation value is not an operator, it's just a number. And it might be a matrix, but you've got to remember that all operators are matrices, but not all matrices are operators, okay? And the commutation requirement only holds for operators. So when I'm dealing with expectation values, they're really just numbers, not operators, and I can move them to either side of anything that I want, okay? So anything that's got an expectation value in here, I can reverse the order to make it convenient. So let's expand this out. AB has to stay the same because it's a pair of commutators. AB expectation value is convenient, so we'll leave it as it is for now. The next term over here is the expectation value of A times B, and I can reverse the order of that. So we can write it as B expectation value of A, because only B is an operator, the other one's a number. And our product of expectation values, we could write in order, any order we like, and it's actually in an order I like at the moment, so let's leave it as it is. And then we got to deal with the other four terms. So BA is a product of operators. It's got to stay in the same order. So it's going to be minus BA. Then we've got minus B times the expectation value of A, and it's in an order I like. So the minus becomes a plus, and we've got B expectation value of A. That minus becomes a plus because there's minus and the minus in front of the bracket. Then the next term, what I'd like to do is actually bring the A in front of the expectation value of B. So this is now going to be plus A expectation value of B. And then the last term in there is the product of the expectation values. They're now both numbers, and I can just change their order. Okay, so this is going to be plus expectation value of A, expectation value of B. I can walk through here now and start killing terms, right? The what have I got wrong in here? Oh, okay, I've got a sign error. Um, this times this should be a plus, so this must be a plus just here, and that means that this term here is going to be a minus. Okay. Um, Again, another good example of having a look and going, hang on, something's wrong here. Let me check it, find it, and fix it. Okay. You want to be thinking like that when you're doing problems, particularly in exams, because it stops you from ending up in traps. Okay. So I know that my product of expectation values should cancel, which is why I knew that. So these cancel each other. These cancel each other. These cancel each other. And all I'm left with is AB and BA, which can't cancel each other, even though they've got a different sign because operators can't be swapped in order. Okay. So what I'm left with here is AB minus BA. And of course, you remember that that is basically just the commutator A comma B. So what we've gone and shown here is basically that A bar B bar is equal to A comma B. In other words, if we take two operators and we shift them back to a mean of 0, the commutator doesn't change either. Okay, this is quite an important result for tomorrow because I'm going to want to be able to do both. I'm going to want to be able to take, I want my uncertainty principle to be as general as possible, right? Which means I want it to be able to deal with uncertainty for an operator at any particular mean I want, but to actually derive that becomes rather tricky because you've got to deal with all these different means. If you can take any particular operator and consider it back to being something at mean 0 and have it conserve commutators and have it conserve uncertainties, then all you've got to do is derive your uncertainty principle from the perspective of operators with mean 0 and know that you can always extend that from anything else back to that. Okay, so that's where I'm heading with this. Couple of extra notes. One is that all operators are matrices, but not all matrices are operators. Okay, so keep that in mind. Sometimes you can actually swap the order of two matrices as long as they're not operators. And what we know are operators are things that are linked to observable quantities, right? Expectation value is not an observable. It's not an observable because it can't be measured in a single shot manner, right? In the same way that I can ask, what is the position? I can't just go, what is the expectation value? I have to either do a large number of measurements to get the expectation value, or I have to calculate the expectation value. Okay, that's why the expectation value is not an operator. And what I'm going to do just before I finish is leave you with one last point, which is that not all statistical distributions that you will see in quantum mechanics, actually not all statistical distributions that you will see in anything are Gaussians. And so one thing that I often see is students getting into the habit of thinking, well, I can take a standard deviation for a Gaussian, so why can't I take a standard deviation for some distribution that looks like this, or a Poisson distribution, or whatever you want? We've got to be more careful about it than that, okay? So generally when we talk about uncertainties in physics, we're usually talking about uncertainties for variables that are distributed in a Gaussian way, which is quite a lot of them that we would measure. But you should be a little bit careful about how you define uncertainty when you get into distributions that are not Gaussian. And to give you one good example, if you start solving Schrodinger's equation for the atom, because of the spherical symmetry, you often get probability distributions that, rather than being Gaussian, actually have a very close peak and a very long tail. Okay, and there you need to be a little bit more careful about what you mean by uncertainty, because it's not quite as simple as just the standard deviation, because you've got a non-symmetric distribution. Okay, just a warning, you won't come up against them very often, particularly in undergraduate courses, but they are out there lurking for you at some point to try and trip you up. So we'll finish there, and then we've got one lecture to go, which is on the uncertainty principle, and I'll see you then.